Yeah, so this paper, as mentioned, is kind of really focusing on how to build iOS or app native LLMs that can help you navigate to do perform different tasks within your screen, how it can understand reasoning. I think they have a nice picture of all the functionality here. So if you think about your iPhone, right? If you want, yes, this is like literally from Apple. They have an iPhone outline here. So it has various different types of tasks in terms of elementary, which is just mainly identifying widget classification, icon recognition, and OCR. Then grounding. So yeah, they've split it up into these different groups. Finding widgets, finding icons, finding text, and widget listing. And it kind of goes through and like helps select different icons, perform different actions. Yeah, so this is just kind of finding elements on the screen. And then this one is more of identifying different things also on your screen. And then this is more with taking everything that's on your screen and then understanding it and allowing you to interact with it. So yeah, questions such as how do I navigate to games? I want to share the reminders app with my friend. What should I do? So this is kind of a few more steps they kind of walk through. Once you have the OCR and the grounding and kind of understanding the user's intent, they plug this in with an LLM that understands obviously the functionality of everything on the screen to answer questions. And then yeah, high level function of the screen. Please describe the screen in detail. So yeah, they walk through all of these different types of tasks. And I think one of the main things that this paper focuses on just is like how to do the vision side of things. So they said that they use a clip plus a VLIM. I think that's it. I'll check one more time. They use a Vicuna model as well as some other. The link visual model is they use both open source LLMs, Cog Agent, and GPT-4V. Compared to GPT-4V, Ferret-UI demonstrates superior performance on elementary UI tasks. Notably, in the context of advanced tasks, Ferret-UI surpasses both Fuyu and Cog Agent. Yeah, okay. I don't see what the vision model was. 1 second, I can look through it a little bit now. But yeah, one of the main things that they do really is just how to effectively understand all the super granular data. So they work on something called any resolution in this, which effectively allows. It's kind of a system similar to a lot of other techniques in CV where you can do different dimensions, zooming, panning, and like crop sizes on your screen, so that you kind of get the full resolution on any image you're looking at. So yeah, that's what they said. Like one of the big issues with these directly resized low resolution global images is that it loses important visual signals that are essential for screen understanding and interaction. And other works targeting directly at the UI tasks have primarily focused on processing entire screens as singular input. And it only supports referring tasks with one bounding box in the input. Yeah, furthermore, the tasks studied in these work do not comprehensively cover all dimensions of UI screen understanding. So they're really working on how to improve that resolution understanding of kind of all elements on the screen being identified. I think that's one of the main things they do. And then, yeah, and then they also kind of spend some more time on this idea of grounding. So how it can identify these locations in the screen with respect to everything else to kind of give you, detailed navigation and so forth. Yeah, so in this paper, they present Ferret-UI, the first multilingual language LLM designed to execute precise referring and grounding tasks to specific UI screens while adeptly interpreting and acting upon open-ended language instructions. And their main achievements are three things: address the 4-minute limitations by focusing on improved model architecture, data curation, and a benchmark. For model architecture, they use kind of basic open source and vision language models, and then they also do this integration of any resolution, which is breaking up the entire image into a lot of different sub-images, and being able to use that along with their grounding thing in order to figure out the whole visual detail of every element in more detail. Essentially is the main things this paper does. And by doing that, they're able to do better than GPT-4b and some of the other open source that they mentioned. Cool. And their data set is also interesting because, as I mentioned, as you could see at the top, they have a lot of different types of tasks that they're trying to solve. So they create a very robust data set that's able to address all of that. And then, as I said, they break it down into all of these different types of functionality, right? So your phone is going to be able to do, they generate this data for each of these different things: for description, conversation perception, conversation interaction, and function inference. These advanced tasks prepare the model to engage in more nuanced discussions about the visual components, formulate action plans with specific goals in mind, and interpret the general purpose of the screen. And in order to test this, they develop a comprehensive test benchmark. And these includes 3 tasks from Spotlight. Yeah, so I mean, I think this is just cool because like this is literally what you're going to be seeing in your iPhones. It's in like some relatively short period of time, I'd imagine. Where was it? Yeah, so these are kind of all the different things that they do. So in Spotlight, they do have a component called Screen to Words, widget captioning, and tape perception, and conduct evaluations against all of these different UI understanding models, including Cog Agent, Fuyu, and GPT-4b. Observe that Ferret-UI significantly surpasses the base Ferret model, illustrating the importance of domain-specific model training. And compared to GPT-4b, Ferret-UI demonstrates superior performance in elementary UI tasks. So yeah, I think there's a lot of different, even they do this obviously for mobile, but I think a lot of companies who are doing this in the web domain also have found like differing performance between like OCR in your screen versus like pulling HTML if you're like scraping websites. But yeah, they kind of do a thing of kind of granularly segmenting your entire screen, and then using all of those smaller kind of subpixels in order to identify in more detail what you're looking at and how it works. Cool. So yeah, I think a lot of this paper really is how they do this segmentation. Because yeah, a lot of UI modeling, UI based LLMs is kind of really drives on how well it can understand this image. So if you look at this, right, this is how they do the AnyRes architecture, which is literally like trying to get high resolution on even low resolution like screenshots. So while Ferret-UI base closely follows Ferret's architecture, the AnyRes incorporates additional fine-grained image features, particularly a pre-trained image encoder and projection layer produce image features for the entire screen. For each sub-image obtained based on the original image aspect ratio, additional image features are generated. For text with regional references, a visual sampler generates a corresponding regional continuous feature. The LLM uses the full image representation, sub-image representations, regional features, and text embeddings to generate a response. So yeah, in this image, essentially what they do is they kind of identify each component as a text component or a higher, lower resolution, and then they kind of zoom it in with the appropriate the appropriate resolutions. As you can see here, they figured out that this is, I guess, text and whatever else they mentioned. And they also kind of fix the resolution for each of these in terms of the aspect ratio. Yeah, and that's kind of how you get to the full screen size over here. And also, yeah, as I said, there's this few other parts of it. They have a projector and a visual sampler and also a text. Yeah, so for text with regional references, a visual sampler generates a corresponding regional continuous feature, and then all of these get added in to understanding what each of these components look like. Okay, yeah, so this is what I was mentioning. They use the they have a benchmark against CLIP VITL, which is the pre-trained visual encoder, and then a decoder-only language model, e.g. Vicuna. It incorporates a unique hybrid representation technique that transforms specified regions into a format suitable for processing by the LLM. At its core, a spatial-aware visual sampler is designed to adeptly manage continuous features of region shapes in different sparsity levels. Yeah, so essentially, depending on what each region has, it determines what additional features it's going to be pulling from that region, and which layers that it uses in order to pass those features into the final, into the language model. Cool. To install UI expert knowledge into Ferret, we make two extensions to develop Ferret-UI, the definition and construction of UI referring and grounding tasks, and model architecture adjustment to better deal with screen data. So yeah, this is what we were discussing earlier. They have two different types of tasks. One is just, can you identify different things in the UI? And then also grounding, which actually requires that you have, so this is like you select something and you just need to identify it. Here you also want to identify like where it is on your screen. And they use these different types of tasks for the model training, building up a strong UI understanding foundation for advanced UI interactions. Unlike previous MLLMs that require external detection modules or screen view files, Ferret-UI is fully self-sufficient, taking raw screen pixels as input. And this way it's able to yeah, the UI screens are predominantly characterized by aspect ratios that are more extended compared to those found in natural images. This is because they've built this out for like any screen dimension. So they work on kind of fixing those aspect ratios and like zooming in and out on different components that are important. Yeah, for example, many questions focus on icons that occupy less than 0.1% of the entire screen. Thus, relying solely on a single directly sized low resolution global image can lead to significant loss of visual details. So yeah, that's where they come up with this any resolution thing. Some of these other papers, I suppose, had done it in Sphinx, Lava, Next, and Monkey. We opt for two grid configurations, 1x2 and 2x1, which are chosen based on the aspect ratios. Given a screen, the grid configuration that most closely matches its original aspect ratio is chosen. And then after they resize it, they kind of decode each of them into these different sub-images and encode them separately using the same image encoder. And the LLM then uses all of those visual features with the kind of sub-images with higher granularity than the base image in order to kind of understand the entire image and how to process it for both the grounding and the initial identification tasks. Cool. So as mentioned, they first kind of do this whole data set creation, then they make a few changes to the model architecture, and then lastly, they have the whole evaluation on this. And this is research, so even though it's done by Apple, they do on a lot of different screen sizes. So and they kind of pull. They pull the data from a variety of iPhone and Android devices. Yeah. So as you can see here, they have each of these different types of devices with various resolutions. And then they have these three main tasks, right, for initially screen to words, widget caption, and tape perception. For the guys who just joined, we're talking about a paper that was recently published by Apple Research that's really talking about how to improve UI understanding with the new LLM that does higher resolution. A majority of the paper is focused on how to improve reasoning of UIs, right? So like I think a lot of people have seen like GPT-4V, for example, if you put in a design, it's able to write code or it's able to reason about it. So this is by Apple on how to do a better job answering here. We can go back briefly and then I'll come back. Yeah, it's just building like a better model that's able to one identify all the different components on the screen, and then perform tasks that are both identify different things as well as find things for you, more grounding, and then also conversation, so perception and interaction across all of this. So they've built a large part of this is kind of how to get high resolution images and fix the whole image ratio subsampling, sub images, and also how to do that effectively, right? So they built a thing that first identifies the key components of each of those sub images and then pulls the appropriate features from it. So if it's text, it'll pull the text from the OCR, or it will identify kind of the aspect ratio and resize it appropriately. So yeah, that's what this is. It's called Ferret-UI, and it's able to solve these kind of referring, grounding, and perception tasks based off of the iPhone or Android visual UI. Yeah, so it should be cool because I think Apple is supposed to launch this at some point in their next OS release. Okay, cool. So I think we were on this. Yeah, we already talked about this. So this is just how they are doing that visual embedding, right? So they take the low resolution full image, and then for each of the sub images, they identify like what text is in it, the visual sampler, and then they do text embeddings, and they also resize and create sub images of all the like more important components. Because a lot of times the kind of challenges with previous papers were that you were asking questions about things that were occupying a very small amount of screen, and by trying to embed the entire image and not actually extract all the text and text embeddings, the performance was not as good. Yeah, so that's how it works. And then the Ferret base model is essentially a combination of QUIP VIT and a decoder-only language model such as Lacuna. But they also compare this entire thing against GPT-4V, and yeah, just based on the experiments, they say that it does better. Okay, so that's the overview that we talked about so far. So they also create this data set, right, in terms of Android, iPhone, the resolution, train and test, and they tested on a few different tasks that we just above, the elementary, advanced, and then screen to words, widget captions, and tape perception across iPhone and Android. Yeah, so this is kind of how they created the data set, right? I think this is public from what I understand, the Spotlight task data set. Take these different things, screen to words, widget captions, tape perception from the existing Spotlight tasks, and reformat them into conversational QA pairs. So 3.5 Turbo is used to create a varied set of prompts from base prompts we author for respective tasks, right? So screen to words is provide a summary of the screenshot. For the interactive element, provide a phrase that best describes functionality and predict whether this UI element is tappable. Yeah, I don't know if this is actually a word, but tap perception is kind of how they define it. And they take kind of this data set and now just add all of this natural language, so it's able to understand human-like questions in more detail. And this kind of just goes through that data set generation in a little more detail. So this is when it's detected on your screen, right? All the different icons, elements, their bounding boxes, etc. Then the widget listing, if you say list all the UI widgets in screenshot, it kind of goes through this entire list and is able to identify that. The grounding tasks, find different icons, locate the text camera, shortcuts tab, etc. And then elementary task overview, again, pretty similar. What kind of icon is the UI widget? Add. Yeah, you can kind of read through this, but this is how they take each of these screenshots and not manually, but create a data set across all of the data. Yeah, so this is how they created their data set. UI detector outputs all detected elements with each element's type, text, and bounding boxes. These detections are used to create training samples for elementary tasks. For grounding tasks, we use all element detections to create one sample for widget listings, whereas the remaining tasks focus on one element at a time. We separate the elements into icons, text, and non-icon text widgets. Cool. Yeah, as I said, like this is the paper hasn't focuses mainly on I would say incremental improvements on all of these things, but I think the final result is something that does really well. But the main thing that I think they've done differently is just think through all of the data set generation plus the how to fix the resolution issue. And yeah, and then they run all of the tests. But I wouldn't say there's something super unique or exciting about this. Cool. And then the last one is how they kind of create data sets that do the whole perception side of things for how to understand and like answer different questions, right? So this one again has more of the prompting slash being able to respond, understand to users' questions, right? So if you have a question, yeah, they have this prompt, you're a visual AI assistant, et cetera, et cetera. Using the provided text and coordinates, design question and answer pairs, and then they give you like a lot of different input boxes, right? And based off of that, it's able to generate like a data set for these evaluation, right? So the user says, I would like to create a new shortcut. And then the system says you can click on this with these coordinates. I'd imagine once they actually deploy the system, it'll just like click on it for you to create a new shortcut. How do I search for a specific shortcut? Want to read some books, etc. Cool. Any questions or thoughts so far?
So here with the data set, did the team build this annotation by themselves and then started training? Or was it available in the open source data set what they have used?
I mean, I think they did it in two ways. They first built out the identification components, right? So it looks like they actually they like generated this data. So they didn't like do it manually. They used a UI detector to generate all of these type text bounding boxes.
Okay, got it. That's it.
Yeah. Yeah, so as you can see for each one, right? So they took a lot of screenshots, right, for spotlight tasks and used paired screens and UI elements mentioned in 4.1 to generate data for novel UI tasks that rely on grounding and referring capabilities. And they come up with more tasks, right, for widget referring, widget listing, find text icon, referring tasks is one with the bounding boxes in the inputs, while grounding tasks are the ones with bounding boxes in the outputs. Yeah, and then for each task, we also use for 1 second. Cool. Yeah, so okay. So yeah, that's pretty much how they create the data set. And then as I said, they break it up into these different groups, right? The classification, which is referring, like identifying things, and then grounding tasks are the ones that tell you where things are, and referring tasks, like click on something and asks you what it does or something. And then the advanced ones are ones where you're trying to like reason about functionality or how to do flows and so forth. So to incorporate reasoning abilities into the model, they follow Lava, and additionally collect data of 4 more formats using GPT-4. Focus on iPhone screens for this part of the data collection, filtering our examples to those with more than 2 but fewer than 15 detections, are sent together with prompts to GPT-4 to create data of the desired format. Cool. So yeah, this is what we just talked about. Is like how they use the prompts in order to generate these more complex reasoning questions. And then yeah, so this is kind of how the final evaluation, right? So Ferret, I think is the model Apple's been working on for a while. So they've launched like a base Ferret model a while ago, and now this paper is the Ferret-UI AnyRes that's able to like essentially do all of the zooming to better understand like resolution and detect these components and grounding better. And then they have these different benchmarks for iPhone, Android, and different types of tasks. So you can see kind of the results. Yeah, and then the rest is just kind of just going through all of that in terms of all of these tasks for OCR, classifying icons, widgets, finding text, responding to text, etc. Yeah, any questions? Ferret-UI outperforms Ferret and GPT-4 on most elementary tasks except for iPhone find text, while GPT-4V demonstrates decent performance on iPhone tasks. Its performance on Android tasks, especially grounding tasks, are significantly worse. Android screens have numerously more smaller widgets, making the grounding task more challenging. Furthermore, Ferret-UI's zero-shot performance on the referring expression comprehension tasks from UIBird when we frame it as defined widget tasks. Cool. That's the main part of the paper. I mean, I think it's cool mainly because like, yeah, it's features that will probably be rolled out in iPhone in like a year, or not even a year, a few months maybe. And yeah, any thoughts? Again, I'm not like into the multimodal space that much, though. But I just thought this was an interesting read.